Hi everyone. So this is our second example. This is one of my favorites. It combines inclined planes and pulleys. Let's get right to it. It says, provided that mass 2 is greater than mass 1, identify the forces acting on each mass, draw the corresponding free body diagrams, and label the direction of motion for the entire system. In other words, we have to set it up. We have to find the setup for the problem. And when I was in college, physics major, I discovered this is the hardest part. This is where we really do physics, when we set up the problem. The rest is just math. So let's practice setting it up, okay? Um, as we established in the past, the key is to draw a free body diagram for each of the masses because we treat them as being independent from each other. Now we can start by answering the last question, identifying the direction of motion. Just because we know mass 2, it's larger than mass 1, therefore it's going to move like clockwise about the pulley, kind of like this. So we're going to label acceleration going down as positive. That's why I have my coordinate plane over here for mass 2. And mass 1 is going to move kind of like northeast, so that'll be our positive x direction. Don't forget we established or we select positive based on the natural direction of the system, so like this. Therefore this is we can have an acceleration like that, positive. Okay, now we can start with the free body diagrams. Let's start with mass 2 since it only has component along the y direction. Do it over here. Draw a vector for the weight of mass 2. There you go. And then let's draw our vector for the tension pulling on mass 2. You got to make sure it's unbalanced, right? Because it's moving. Now we can label. This is mass 2 times acceleration due to gravity, and this is the tension. Now I'm going to label the forces on the drawing as well. I think it'll be beneficial for us to see what's going on. So there you go. Let's label again. This is M2G, and this is T for tension. There you go. That's it for mass 1. We don't have to break anything into components, right? We only have components along the y direction. Now let's work on the free body diagram on mass 1. There you go. This is the center of mass. And we have the weight of the object. Don't forget that it's always pulling down, straight down. So like this, from the center of mass. Then I'm going to copy that vector, my free body diagram over here. And then I have the normal force perpendicular to the surface. There you go. Copy this one for my free body diagram. Since it's moving, right, like this, don't forget that friction always opposes motion. So I need a vector for the force of friction. Now since it's moving, I hope you remember this is kinetic friction. You'll see why this is important. There you go. Now let's label. This is the weight of mass 1. This is the normal force. Now instead of force of friction, just like this, F sub F, I'm going to write it using the equation we learned last time, which is mu sub k for kinetic times the normal. So mu, let's do it again. Mu sub k times the normal. Very good. Now this is completed. We have to break it into components because now we don't have just x and y direction, because the weight has a different direction, not like only y or x. So for that, we're going to apply Newton's third law of motion. Since this mass is only moving along the plane, not up or down, right? We need a force which is acting against the normal force. So like this. Very good. There you go. And I missed the force of tension, right? Because it's pulling on mass 1. There you go. Now the force of tension, it's going to be the same because we have the same cable. So this is the force of tension. Let's go for my free body diagram. There you go. And this is tension. Now I need to label this one over here. And since I have a vertical component or a perpendicular component of the weight of the object, I need a parallel component over here as well. So I'm missing another force on this side. You'll see how, or you'll see why. We have to use trig, okay? Because if I copy this one, I think I'm going to copy this one instead. And I complete my triangle using tip-to-tail method. I can solve for the parallel component and also the perpendicular component of the weight of the object. So there's our 90-degree angle. And then notice this is theta, so the corresponding theta will be here. This is the opposite of theta, and this is the adjacent. And this is the hypotenuse, which is the weight of the object, okay? So let's use trig, then I'll clean this up right now. So we start with sine from SOHCAHTOA. Sine of theta is equal to the opposite divided by the hypotenuse. Let's substitute. The sine of theta will be opposite, we don't know it, divided by the hypotenuse, which is the weight of mass 1. We're trying to solve for the opposite side, so by doing some algebra, we'll have the opposite side is equal to m1g sine theta. That's it. So this one, we need to add m1g sine theta. Let me do it again. m1g sine of theta. There you go. Now let's find the adjacent side, which will correspond to the force acting against the normal. So cosine of theta is adjacent divided by the hypotenuse. We'll do the same thing. Cosine of theta is equal to the adjacent side divided by the weight of mass 1. Therefore, the adjacent side is equal to m1g times the cosine of theta. So this side is m1g times the cosine of theta. And now I can clean this up. I need this, I don't need this. Oh. There you go. Now I'm going to label my drawing. So this is the weight of mass 1. This is m1g cosine theta. Now, instead of writing mu sub k times the normal, I know that the normal will be equal to m1g cosine theta because they're canceling each other out. So this will be mu sub k m1g cosine theta plus m1g sine theta. No, it's too far apart. There you go. So I have my kinetic friction plus the parallel component of gravity. I have tension, normal force, and to label this one. I have the weight of the object, tension, and weight of mass 2. Now let's identify which one is positive, which one is negative, so we can sum the forces. We established that this is the direction, the positive direction, right? So for mass 2, down is positive and up is negative. So tension is against the motion. Now the natural motion will be like this, which is the direction of tension. So this is positive and this is negative. Now just as a formality on the y direction for mass 1, this is positive and this is negative. Now we can sum the forces and do that over here. Let's start with there you go. With mass 2, since we don't have a lot going on, just y direction. So the sum of the forces acting on mass 2, since there's motion, will be equal to mass 2 times an acceleration, which is equal to, this one's positive, so m2g minus the tension. There you go, that's it. Now let's work on the y direction for mass 2. So mass 2 in the y direction. Well, there's no motion, so it's equal to 0, right? Because it's not moving along this plane. So it'll be normal force minus m1g cosine theta. Established as negative. Now let's work on the forces acting on mass 2 along the x direction. There is motion, so we have mass, not mass 2, that was mass 1. Mass 1 x, so mass 1 times an acceleration will be equal to the positive, which is the tension, minus, now parentheses, because we have to add these two together. So it'll be mu sub k m1g cosine theta plus m1g sine theta. And there you go. We have the setup ready. Of course, if we had the mass and the coefficient of friction, we could easily, and the angle, we could find all the forces. But this is the setup. The key is identify the direction of motion, label that as positive, natural direction. Look for the forces, break it into components, make sure you have your free body diagram. You need to account for all the forces, right, present, otherwise it will be incorrect. And that's it.